Hello, my name is Daniel Gustafson, and this is Lab 5. To start things off, the purpose of this experiment is to see how Faraday's law is used in everyday life. For the case of this experiment, we will see how it is applied when a magnet is dropped down a conductive tube, such as a tube of aluminum foil or a copper pipe. Applications of Faraday's law in our daily lives includes new EVs, electric generators, and wireless charging in cell phones. We are going to perform this by collecting observational data, creating a computer program to visually show what is happening, and then comparing our computation results with our observed data. This experiment is very simple, as you only need a few things that you could very easily find in your own home. You'll need a bar magnet, preferably one that you've been using for the past few experiments, as that'll make the computational model easier. For the main item, you'll need a roll of aluminum or a copper pipe. Lastly, you'll need something to time how long it takes for the bar magnet to fall through the tube. This can be your smartphone or watch. Before moving to the computational model, make sure to take the measurements of the tube, such as the length, the width of the metal, and the inner radius. Our procedure for this experiment is also very simple. First, take your copper pipe or tube of aluminum and make sure it's completely vertical. That way, we can decrease as much potential friction as possible. Next, make sure your timer is ready, and then drop the magnet down through the tube. Once the magnet makes it to the other side of the tube, stop your timer and write down your time. Repeat this until you have 5 times. Before dropping your magnet down the tube, make sure to take note of which way your magnet is facing. If it is not labeled, mark an end of the magnet with an N to represent north. Running this experiment, my average time between 5 trials was 12.86 seconds. My tube dimensions were a length of 100.5 centimeters, an inner radius of 1.3 centimeters, and a metal thickness of 0.1 centimeters. As for my magnet, it has a mass of 23 grams and a magnetic dipole moment of 4.1 amps per meter squared. Moving to our computational model, we get this graph in pipe with red and blue rings above and below the magnet to distinguish the direction of the current. First, looking at the graph, at the beginning and the end, the slope represents when the force due to gravity is greater than the magnitude from the magnetic dipoles created by the magnet and the copper pipe. Our code takes a very long time to render the full pipe, so I reduced the length of it by 75%. However, looking at the graph again, once the magnet gets into the tube, we can see that it flatlines. This is because the force of the gravity and the force of the magnetic dipoles are now equivalent. The magnet is no longer accelerating but has a constant velocity downwards. Moving to our pipe on the right, we can see a red and blue ring, which represents which way the induced current flows from the magnetic flux going through the pipe. We will get more into that here in a moment. My current calculated mu magnitude of my magnet is 4.1 amps per meter squared. Using my code to predict the exact mu magnitude needed to get the same time as my observations, it would need to be 4.6 amps per meter squared. We now have a simulation that allows us to visually see what is happening while the magnet is inside the copper pipe. But what does this actually tell us? Well, let's find out. First up, which color corresponds to clockwise and counterclockwise when viewed from above? Here we can use Lenz's law in the right-hand rule to figure this out. We'll start with blue. Since it is on top, the magnet is constantly moving away from it, meaning the magnetic flux is always decreasing. With that, we can use our fingers and imagine them coming on top of the magnet, almost thinking of them helping push the magnet down. With that, we stick our thumb out to determine the current direction. Here, our thumb is pointing to the left, so the current for blue will be going in the clockwise direction. Red will be the opposite, as it is flipped from the blue. What happens when we flip the magnet around? The direction of the currents will just flip, but everything else will stay the same. How does the recorded observations compare to the computation model? Our observed average was 12.86 seconds, while our computed time was 10.252 seconds. Some sources of error could be ignoring air resistance, human error, and not timing it correctly, such as stopping the time when the entire magnet is out of the tube and not when it first reaches the end. Lastly, what does the shape of the velocity versus time graph tell us about the forces acting on the bar magnet? The graph tells us that at the entrance and exit of the pipe, the force from gravity is greater than that from the magnetic dipole moments created, but once the magnet is inside the pipe, they are equal to each other. Lastly, we'll wrap up the lab with a few what-if questions. To begin, what if the resistivity of the conductor was reduced as close as possible to zero? How would the dynamics of the falling magnet change? When we take a look at Ohm's law and rearrange to solve for current, as resistivity gets smaller, current gets stronger. So, as resistivity gets closer to zero, current gets stronger. If it were ever to reach zero, the current would be infinite, meaning the magnet would essentially float as soon as it enters the pipe. Moving to the next question. If we were to make cuts or holes in the tube, our rings from Lenz's law would be interrupted, meaning the strength of the force from the magnetic dipoles would be extremely weaker, letting the magnet fall much faster.